Okay, lecture AP 1.2, and we're talking about today precipitation analysis. Up until this point, we have been using the mole concept to do analysis of percent by mass and using molarity to do previous 1 through 3 questions. And we look specifically how we look at the individual species or the individual components of a salt and determining their molarities based on the ratio of ions they break apart. Now we're continuing now to talk analysis of compounds through gravimetric titration, through comparing one compound with another, but now we're using precipitation analysis. Okay, and that's what these next questions are based on. So we're going to do them, and I'm going to model them for you. You should have tried these first. You should have struggled. If not, if you've conquered them, great, you don't need this. Okay, but this is a reference for these types of problems. Okay, what mass of silver chloride will be recovered? Okay, silver chloride is a classic precipitate based on an important solubility rule. Chlorine, all halogens except for fluorine, so chlorine, bromide, and iodide, okay, are all very soluble. Now, what does that mean, soluble? That means if their ion, for instance, sodium chloride, all right, is dissolved in water or placed in water's presence, water's negative ion can compete, okay, it's a negative ion, can compete for the positive ion, and its positive part of its molecule can compete with the negative ion. What I mean by that is if you have a crystal of an ionic compound, you have a sodium plus, you have a chlorine negative. Okay. The ionic attraction or the Coulombic attraction exists between a positive and negative. Now, what happens is water can get in there in between those. For instance, the negative part of the water, of course, the oxygen end, can get in there and encircle this ion, and thus this ion doesn't feel this negative anymore and can be brought away and thus dissolved. Same thing over here. The positive part of water can encircle it, as we learned in honors chemistry, and that can be said. But what we're saying here is that the attraction between the ions, okay, has to be the same or weaker than the attraction between water and the ions. Now, what makes the attraction between these ions the same or weaker than the attraction for water? Well, it's really something called the charge densities that I've been talking about. These are pretty big ions, so therefore their charge density isn't so great, especially being +1 and -1. Not many, if I can remember, any +1 or -1 ions are insoluble. Okay, if you look at calcium, okay, oxide, quicklime, these guys have stronger Coulombic attraction, and these guys are insoluble. Well, why? Well, because the +2 and -2 makes the lattice strength of the ionic compound stronger, and the reasoning behind is calcium had to lose 2 electrons. So when it was an atom and when it became an ion, it got even smaller by losing 2. So the charge density is really high here for calcium +2, and that type of understanding explains a lot of the chemistry with the group 2 ions, why they're mostly insoluble, and when they are soluble, they're strong bases. We'll get to that. Fluorine, back to the designation here, fluorine is one of the smallest ions or atoms there is. Now we know that fluorine becomes a fluorine ion, it gets bigger because of more electron-electron repulsions, or electrons outnumber the protons, but in any case, it's still a pretty small ion. So being small ion, this -1 is countered by its smallness, which means it has a pretty high charge density for -1. So fluoride compounds are generally insoluble, okay, and don't dissolve. These are pretty soluble. Oops, got a doohickey there. Get rid of the doohickey. I'm not sure what that really means, but it comes out that way. So these guys are very soluble. Now there's some exceptions. The exceptions, and we did a lab last year, remember these important exceptions are silver ions, okay, lead +2 ions, and that dimercury ion, okay, or mercury 1. These guys, when in contact with these, form Coulombic attractions that are greater than what water can compete for, thus they say solids. Okay, a little background information. okay, as we get to the most important type of chloride. Silver chloride is picked upon often about something insoluble. And we'll talk more about the rules. So let's get rid of a lot of this and get back to the problem. Certainly, if you want to keep looking at this, you can rewind the video. I'm having a tough time. Okay, here we go. Okay, so getting rid of most of this, and just quickly, oops. Okay, moving on. Okay, getting back. Let's change some color. All right, here we go. So what mass of silver chloride will be recovered if excess sodium chloride solution is added to a certain amount containing a molar? Big M is molar. Okay, so they want to know how much silver chloride will be recovered. How much will precipitate out? So we're going to add sodium chloride, which for the reasons we just explained is very soluble, into a solution. Okay, notice the waves of 595 milliliters of a certain molar solution, 1.75 times 10 to the negative 2. Never understood why they use scientific notation for such small, reasonable numbers you can write in any case. So that's the molar solution. So they want to know how much. So they're giving me the molarity, they're giving me the volume. Very quickly I can get the moles, how many of them. But we're using what mass will be recovered. Now they said excess, and that's very important you understand this, because if we're not sure, okay, of how many, in this case we kind of do, but we're adding enough sodium chloride to make all of the chloride ions, in this case all of the silver chloride, to precipitate. Okay, so clearly what we're doing here is we're adding chloride ions, because sodium chloride breaks apart into Na plus and Cl negative. So clearly we're adding chloride ions into a mixture that already has silver ions, and we're going to precipitate it out. The question is, all right, what mass of silver chloride recovered? Well, this is a gravimetric titration because we're going to use the amount of silver ions in it to figure out the mass of silver chloride, or in this case, the number of chloride ions necessary to do it, okay, although we're not getting that technical. So certainly you have molarity, and you have moles, volume, which will have to be in liters. We have these two things, we solve for moles, and we know that for every 1 mole of silver ions, we have 1 mole of chloride ions, because silver chloride, Ag plus Cl. So with that being said, you can do the problem, not in this fashion, and I would like you to try to think along these terms. It's dimensional analysis, okay? At some point, I just want you to get the question right, so at some point you decide what's easiest for you. In any case, I'm just going to start with 595 milliliters. I'm going to get rid of my milliliters, and I know that for every 1,000 milliliters, I have a liter. And that gives me a liter. And the reason I'm going there is I'm going to use my molarity as my converting factor. And there's how many moles? There is 0.0175 moles. I'm getting that from this number for every 1 liter. Now I have moles of what? Well, this was 595 milliliters of Ag plus ions, like silver nitrate or something. Okay, and I'm left with some stoic. Since Ag plus is up top here, for every 1 Ag plus, there's 1 silver chloride. That will not always be the case. Okay, in this case, it's a nice easy 1-to-1, and you probably could get away without writing that, but it's good practice to keep track of your stoic. So your silver disappears, and what you have is moles of silver chloride. Now I'm going to get rid of my drawing because I don't need that anymore and continue this out. And the last thing I'm going to do is I'm going to find grams since they wanted mass. Notice my moles up here, and 1 mole is how many grams? Okay, well, silver chloride, I've got to look up. Okay, so silver, for my periodic table I just had to grab, my silver is 107.87, and my chlorine is my 35.45. All right, and we're going to add those together, and if you haven't already done so, 107.87 plus 35.45, I get 143.32. Okay, mole goes away, and I'm left with grams. Let's put that in a calculator. And 595 divided by 1,000 times 0.075. Okay, times 1 divided by 1. Okay, times 143.32. And I get my answer to be 1.49 grams. And who's left standing? Grams of silver chloride. There we go. 3 significant figures. That was 1.492, and I just rounded. Okay, and that's we could figure out from this mass experimentally. If we were to collect this mass, we could go backwards experimentally and figure out the ratio of moles to moles and build the formula as we've been doing. Okay, all right. So number 5. We'll just continue on to the problem. A pure substance is known to have carbon, hydrogen, chlorine, and now we have a 4-gram sample was burned. That's combustion analysis, and we have some CO2 produced. We know the percent by mass of the CO2 produced, or all the carbon dioxide that was produced. That carbon came from originally the sample. Okay, so we're going to do what we did previously by looking at the CO2 percentage. And then this is new. In a separate experiment, the chlorine contained only 0.25. The compound was converted to silver chloride. There's our precipitation analysis, our gravimetric titration. So we have precipitation analysis, and now we have a on top of the combustion analysis, and we're going to build a formula from that. So let's start by the carbon and hydrogen and chlorine compound. Okay, it was burned. Of course, that's in the presence of oxygen. So I want to write the O2 up here. We do that sometimes. And that's going to give me CO2, of course, in water. Probably some other compounds as well. Since there's a chlorine involved, we'll stick with the CO2. And looking at CO2, we know that that's a 12. Okay, just going to use 12.01. Let's use this significance. 2 oxygens, 16, so that's 32. And that gives me 44.01 grams total. Okay, and 44.01 grams total. We want to do percent by mass of carbon. Carbon is 12.01. Okay, and let's do that. 12.01 divided by 44.01, and I get times 100, but we can skip that, and that gives me 0.27. 0.2729. Okay, obviously it's 27.29 percentage if you want to find a percent, but that's the fraction of mass due to just the carbon in CO2. All right, great. Well, what do we have in the problem? We know that there is 4.32 grams of CO2 produced. Well, I'm going to multiply that by 0.2729, and that's going to give me exactly how much carbon, 4.32, and I get 1.178. So 1.178, and that's 1.78. Probably should round that to 9. 1.179 grams. Let's keep that nice and clean as much as I can. 1.789 grams of carbon. That's an important number. All right, that's from a 4-gram sample. So 4-gram sample. Okay, 1.79 grams of that is my carbon. All right, did they tell me how much water was produced? No, they did not. But I can get my chlorine. Okay, so in a separate experiment, the chlorine contained 0.7 of the compound. I'll be very careful here. This is not the same 4-gram sample. They're saying in another experiment, oops, okay, in another experiment, okay, let's just change the ink here. In another experiment, we used 0.125 of the grams of the compound. So this is a little trickier because we're going to find, okay, how much grams of chlorine from this gram sample, and we'll do a percentage of that and relay it back to the 4-gram sample. Okay, so what we have is the 4-gram sample, and out of the 4-gram sample, we got how much carbon? We got 1.179 grams. Okay, in another experiment, we have a 0.25 gram sample of the compound, and it was converted to 0.334 grams of silver chloride. We can assume in this process that all the chlorine that was in the sample became silver chloride. Okay, so determine the purity formula. So what we're going to need to do here is find how much chlorine is here. Well, I know that the mass, the formula mass of silver chloride we have above, we can find moles, and from moles, we can do a ratio. So let's just do that. So 0.334 grams of silver chloride. I'm going to get rid of grams, so grams goes to the bottom. I want 1 mole is how many grams. I'm converting to moles, and we already did this up here. It was 143.32. So 143.32. Bad planning in my case. 0.32. Yeah. All right. And of course, let's just make that clean. 143.32. 143.32 grams. My grams cancel. I got moles of silver chloride. And I know it's a 1-to-1, but it's not always going to be that way. It's really good to do this. For every 1 silver chloride, I have 1 chlorine. And that way, we get moles of chlorine. And we can get grams, because for every 1 mole of chlorine, notice the moles cancel, I have 35.45. Okay, let's go find that value. So 0.334 divided by 143.32 times 1 divided by 1 times 35.45 is 0.08261. 261, good enough. 2614 is good enough. All right, and of course that's grams. You can hear my son yelling in the background. Sorry about that. Doesn't want to take his nap. All right, so now that we have grams, that's the amount of grams, 0.08264, that came from the original sample. Okay, so left we have to do here. So if you notice, we have the grams of carbon from 4 grams. We have the grams of chlorine from 0.25 grams. So what I'm going to do, because these are 2 different experiments, I'm going to come up with a percentage. That percentage, okay, if you're wondering, my son is sitting with me now, so that percentage, let's do magenta, that percentage I can get out of 100, and if you notice there's 3 what? Oops, I don't want that. There's 3 chemicals, or three elements in this compound. So we're going to get our chlorine. So what I'm going to do is I'm going to find the percentage of each and then subtract that from 100 to get the percentage of chlorine. And once we have the percentages of each, we can rock and roll and get our empirical formulas. Okay, at least that's how I'm thinking. So I'm going to take my 1.179 grams over the 4.00 grams, and I'm not going to times it by 100 because we're big boys and girls. 1.179 divided by 4 and I get 0.2948. That's out of 1, of course. And then over here, I'm going to take my 0.125, and this is 0.08261 over that. I'm just finding a percentage, sort of, like a fraction really, 0.08261 divided by 0.125. And of course, this is a much bigger percentage, 0.66088. Okay, so I'm going to get some stuff out of the way here. We're going to get all this stuff out of the way. And again, if you need to see the work, just rewind the video. Oops, bad Grodsky. Okay, so now we have our two percentages. Let's add these jokers together. Okay, I'm not sure why they're jokers, but we'll add them. Plus 0.2948. And what I get is I add them together, I get 0.955680, and of course 100 minus that, okay, so when I added these together, what did I get? I got my son in my lap, just stay with me, 0.95568. Okay, I'm going to have, I should say 1 minus that. Okay, Brady. Okay, so 1 minus my 0.95568. Okay, so what I get is from this value, let's give me a written device, from this value, I get 0.04432. Okay, obviously, let's convert this to percentages. Okay, this is 29.48% carbon. This is 4.432%. Who's that third one? That's your hydrogen. And this, of course, is your 66.088%. All right, now we've got our percentages. You can now start working on the empirical formula. Let's get some more stuff out of the way. It is clear to me that I did not give you enough space to work on this problem. Okay, so let's continue with another ink. And here we go. So we've got 29.48 grams. I'm assuming a 100-gram sample of carbon. I've got 4.432 grams of hydrogen. And I've got 66.088 grams of chlorine. Okay, get some more stuff out of my way. Well, let's convert to moles. All right, carbon, we know that for every 1 mole, we've got 12 grams. I'm not really considering the precision, okay. And then, of course, this one, bad planning, Grodsky. Okay, so let's do that. 29. What's up, Brady? 29. So we got 29. I'm going to have to pause again. All right, so I'm converting to moles. So convert to moles. I'm dividing by 12, and that gives me 2.457. Again, I don't have to use the exact values given to me here because we're finding ratios. So I'm just going to make it simple. This divided by 1 is 4.432 moles of hydrogen moles of carbon, and then of course 66.088 grams divided by 35.45. That one I did because I just never know what to do with that one. Okay, is 1.864 moles of chlorine, and now I need a mole ratio. Divide by the smallest number. 1.864 divided by 1.864 is our 1. And then 4.432 divided by my 1.864. 4.432 divided by 1.864. That gives, all right, 4.432 divided by 1.86 clearly is 2.37, and 2.457 divided by the smallest, 1.864, gives me 1.3. Now these ratios are not nice, but they clue us in because it looks to be that we're off by a third. We can't round this third off with this 0.37. This 37 is nasty. Okay, so what we're going to do is change my colors. And I think that I'm going to do here is I'm going to multiply everything by 3. Okay, when I do that, 3 times 1.3, okay, is 4. So we got 4 carbons. And then, of course, 2.37 or 2.3 times 3 is about 7. And then 3 times 1 is 3. So, again, I multiply everything by 3 to get nice whole number atoms. Can't have 0.3 of an atom in our empirical formula. So that leads us to C4, H7, and 3 chlorines. All right, enjoy that one.